this next example, we're going to solve a traveling salesman problem using the cheapest link algorithm, but on this one, the weights are going to be given to us in a table as opposed to in a graph. So for this next example, Curiosity is a 2.5 billion rover that roams around Mars in a region known as the Gale Crater. There are 7 locations that the rover must visit, and the starting location is G1, the landing site. The numbers in the chart represent the distance in meters between locations. We're going to find that cheapest link tour and determine the distance to complete the trip. Now again, my expectation is when you solve these types of problems, you're going to record the weights in the order found. So I will have that in the directions on your exam, so just kind of keep in mind that that is going to be the expectation. Now this one's going to be a little bit different than that nearest neighbor algorithm, because on this one, when I only have the weights recorded for me in this table as opposed to on a graph, it's going to be much harder for me to see the violations that I have to keep track of when I'm running this algorithm. So on this type of problem, since it is harder to see the violations of that 3-edge rule or the partial circuit rule, we are going to use an auxiliary graph to help keep track of the connections that we're making. Alright, so we're going to use this thing called an auxiliary graph. So what is that? We're going to put down our vertices like we would be making a graph model for this. So I'm going to have my vertices, and I always like to put them in a circular pattern. So G1, G2, G3, G4, 5, 6, 7. Okay, so but as opposed to drawing in all of the edges, we're just going to draw in edges as we want to grab weights. Now the other thing that we're going to keep track of when we're looking at this is the fact that when we look at this mileage chart, which in this case the mileage is in meters, these are all distances, the axis or the information is repeated across this this line of symmetry right here. So to maybe not get distracted, I don't have to look at all of these weights, I just have to look at one set of them. So I'm going to go and cross off this top set of numbers because all of this information up here is repeated in these numbers over here. So then I just have this one set of data to look at. Okay, so now just using the numbers down here, what is the smallest number that we see anywhere in the graph? Alright, so running through these columns, it looks like it's going to be this 1300. So I'm going to go ahead and record it and then mark it. This 1300 is a connection between G6 and G7. So I'm going to keep track of that on my auxiliary graph. The next lowest number that we're seeing anywhere. Oh, and I like to circle it too to remind myself that I grabbed it. Okay, so the next lowest number I'm seeing anywhere is this 1500. So I'm going to circle it, record it, and mark it. That's a connection from G6 to G1. Now from here on out, we're going to have to keep track of what we're grabbing so that way we don't have a violation of the 3-edge rule or the partial circuit rule. The next lowest number after the 1500 would be what? So looking through all of these numbers, it looks like it's this 2000. Now this 2000 connects G5 to G4. Is there any problem if I connect those two vertices? Nope. We're going to go ahead and grab it, mark it, and record it. After 2000, the next lowest number it looks like it would be this 2200 connects G7 to G1. Yeah, that'd be a problem because I would create a circuit right here. So this 2200 is out. The next lowest number after that looks like this 2800, but I have one here and I have one here. Okay, so here's where when you're running through the algorithm, in the cases that you have a tie, it's dealer's choice. You have to just grab one of them. So let's say, for instance, I grab this 2800 right here. Now, if I wanted to pick it that connects G1 to G4, is that going to be a problem? G1 to G4. Nope, not a problem. Doesn't have a violation of either my 3-edge or my partial circuit rule. So I'm going to grab it and record it. Now at this point in time, if I were to go through these edges, what's the next lowest number that I see? Well, it would actually be this other 2800 right here, right? So now I have to assess this 2800 based upon the markings that I've already done. This 2800 connects G7 to G3. Is that going to be a problem now? G7 to G3. Nope. Doesn't create a circuit, and it doesn't create 3 edges coming out of a vertex. So both of these 2800s are actually going to be okay. So there's where when you have a tie, then once you grab one of them, that you assess the other number and see is that still a viable option, or is that one now going to be discarded based upon the choices that you made previously. The next lowest number after that is going to be this, oh, so I want to mark it. There it is. Okay. So the next lowest number is going to be this 2900 that connects G7 to G4. G7 to G4, yep, that would be 3 edges coming out of G7, so that's no good. After that, looks like it's going to be this 3000, which I have one occurring here, and I have one occurring here. This one connects G3 to G2, G3 to G2, no problem there. So we're going to connect it, grab it, and mark it. Now the other 3000 connects G6 to G4. So notice if you were to try to connect G6 to G4, that one is going to be a problem out of G6. So this one we would not have accepted no matter what. At this point in time, we've hit a very special moment in grabbing these edges. Notice that we have 7 vertices here. So ultimately, when we're done grabbing our circuit, we're going to have 7 edges. So far, I have 1, 2, 3, 4, 5, 6 edges. So I'm only allowed to grab one more edge. So here's where I'm going to look at my auxiliary graph and see what edge I would need in order to close this circuit. It's going to be this edge right here that connects G2 to G5. So G2 to G5. So G2, G5, it looks like it's going to be this weight right here. That's going to be the last one that I need to finish my cheapest link algorithm. The weight of this tour then, if we were to add up all of these weights, is going to be 21,400, and then my units are meters. So that's going to be the distance that this rover has to travel, and then we're going to actually write the circuit. So here's where we're going to keep in mind that the starting location is G1, the landing site. So this rover then could go from G1 to either G6 or G4, so your choice. So maybe I'll have mine go to G6, then G7, then to G3, G2, G5, G4, and then back to G1. And then I would also accept the mirror image of the circuit. So there's an example of running the cheapest link algorithm from weights recorded in a table. We're going to use this auxiliary graph to keep track of whether or not we have violations of 3-edge or partial circuit rule. And then we would just use that then to also see when I need to close my circuit, what edge I would want to grab.